we will take up the application of this flexibility matrix to analyze indeterminate trusses. So, coming to the trusses, the degree of indeterminacy is determined in two ways. One is external indeterminacy. For that, usual procedure we are going to follow. That is total number of reactions minus total number of equilibrium equations. That will give you external indeterminacy, and use the equation n is equal to 2j minus 3. If n is greater than 2j minus 3, that gives you the internal indeterminacy of the process. So, in this particular case, we must be taking both internal as well as external indeterminacy of the trusses. So, directly I will come to the problem, one of the problem, and we will apply the flexibility matrix method to analyze the indeterminate truss. So the problem is analyze the disjointed plate frame shown in figure by flexibility matrix method. Flexibility of each member is, that is, L by AE. L by AE is given to be 0.025 centimeter per ton. Okay, here everything is given in tons. So we will solve it in tons only. The truss given is having the members as shown in the figure. So upper member, bottom member, side members, and two diagonal members. See, this one of the member is not a overlap, means there is no rigid joint at this particular point. And the support on this member is given to be a hinge, and support on this member is given to be on rollers. Right. External loads acting on the truss are given to be 10 tons and a horizontal force of 5 tons. So these two are the loads which are acting at this particular time. Length of the bottom members is given to be 4 meter, and height of the member is given to be once again 4 meter. So this angle happens to be 45 degrees. That is tan inverse of opposite side by adjacent side. 4 by 4 will give you 45 degrees. So now let us go for analysis of this. First, try to determine external indeterminacy. So to determine external indeterminacy, consider the number of unknown reactions. External indeterminacy. So here there can be two number of reactions, one in vertical direction and another in the horizontal direction, because it is given to be a hinge. Here this one is given to be a roller. At the roller, perpendicular to the surface of the roller, there exists only one number of reactions. Therefore, how many number of total reactions? Total number of reactions are equal to 3, and conditions of equilibrium that are available to us is also 3. Therefore, there is no external indeterminacy for the given reaction components. We will try to determine internal indeterminacy. So, to determine internal indeterminacy, in your previous first year level, you are studying one chapter, analysis of determinate trusses. So there they used to use one equation. A structure is said to be internal indeterminate if if n is equal to 2j minus 3, where n stands for the number of members and j stands for number of joints. If they are equal, then we say it as a perfect frame or a determinate one. If n is greater than 2j minus 3 in any particular truss, then it is an indeterminate structure. So here, count the number of members n. So, 2 vertical members plus 2 horizontal members plus 2 diagonal members. So, totally 6 number of members are there. Count the number of joints. As I told you, this is not a joint. 1, 2, 3, 4 number of joints are there. So, determine 2j minus 3. So 2j, 2 into 4 minus 3 will give you 5. So degree of external indeterminacy is equal to 5 minus 4, that is equal to 1. So internally there is an indeterminacy, that is one member is given to be more. So you need to remove that member and assume that as a redundant force and apply the basic principles of flexibility matrix. We are going to determine that particular force in the member. So I am going to release this structure. Releasing means I will make that determinate. How to make it determinate? Remove any one of the member, either this diagonal member or this diagonal member can be removed. So now my determinate structure will be a release structure with a roller support and a hinge support at A and external loads of 10 tons and 5 tons. Right? I am going to relieve this particular member. Now it becomes a determinate one. And I assign a coordinate number 1 for this particular diagonal member. So this structure, you can call it as released structure. Means I am imagining that this member is being released. So this is called release structure. Now, after releasing the structure, we will analyze for the forces in the members of all except redundant one by means of using either method of joints or method of sections. So you have studied in your second semester about analysis of trusses. Same principles are being adopted to determine forces in all these members of the structure. So we will use the name for the joints. Upper member U1, U2, then lower joint L1 and L2. So now I am going to have a table before I go for the analysis of determining the forces in the members due to external load, and after applying unit load in coordinate direction 1, we can enter all the things in a systematical table, and then we can develop the flexibility matrix. Later on, we can solve for the final forces in all the members of the truss. So, I would like to have a table. So, have a table like this. Determine in the first column name of the member, force due to external loads in the members, that we can call it as S. Then force due to application of unit load in coordinate direction 1, that I call it as S1. Then S1 square is required. You can square the value of S1, what you get? Then S into S1 is also required, so have one more column. Then you can have one more column for net force. Now, delineate all the members referring to this. So, this member, I can call it as L1, U1, L1, U1, and so on. So, we will call the number as L1, N2, then N2, U2, L2, U2. Next is U1, U2. That is, this member is L2, U2. Similarly, U1, L1. U1, L1 stands for this member. Okay, U1, U2 you can have. Then member L1, U1. Then member L2, U1. And last member, there are 6 members, L1, U2. See, due to the application of the external load, what are the forces induced in all the members? That you need to find by means of using either method of joints or method of sections, whichever you feel easy. I think method of joints is quite easy, even though it is little bit lengthy. You feel that. So now I will have one figure. I will remove this member and I will keep only the determinate structure. So whatever redundant force I assume, I am going to remove that. Now we will go for analysis of S force. So next headline we can say analysis for forces in members. Forces in members. U2 external load. Right. U2 external load. So now you need to determine reactions first. To analyze the forces in the members, determine the reactions. I will call this as R1 and this reaction as R2, and there is a horizontal reaction at N1. So call this as N1. Right. So now I am considering this particular structure and analyzing for the forces in the members. So in method of joints, you must select a joint which has got maximum of 2 number of unknown forces. See, once you determine R1 and R2, then we can think of determining the forces in the members, because here 3 unknown force members are there, here 2 are there, then here also 3 members are there. Therefore, determine the reactions. You take moment about this point, that is L1, and equate sigma M L1 to 0. So taking moment about this point, R1 and U1, H1, they give 0 moment, because their line of action passes through the moment center. I have taken the moment center as joint L1. So now, due to R2, anti-clockwise moment is produced. So I say R2 into, I am taking anti-clockwise as positive in the left hand side and clockwise as positive in the right hand side. Or otherwise you will write a continuous equation, rearrange it and then find out what is wrong. So this happens to be little bit easy. R2 into 4 gives anti-clockwise movement. This must be equal to the clockwise movement. See, when done, if produced in downward direction, it also passes through this point L1. Therefore, 0. But when done, it turns the in clockwise direction. So I take a clockwise movement positive here. 5 into 4. 4 get cancelled. Therefore, the value of R2 is equal to 5 kilonewton. Now, equate sigma V to 0. That is, all vertical forces, external vertical forces you consider, R1 upward plus R2 is equal to downward load, that is 10 tons. So, determine R1. So, determine R1. 10 minus 5, you get 5 tons. 5 tons you are going to get. So now we have determined the reactions, and next step is to determine forces in all the members. As a figure like this, external loads. Now we will consider the joint which has maximum of 2 number of unknown forces. Because we are having only 2 equations of equilibrium to apply at a joint. We don't have sigma n equal to 0. You cannot apply for the joint. Right. So you have only sigma v equal to 0 and sigma h equal to 0 to analyze a particular joint. So check which of the joint has got only maximum of 2. See, h1 I calculated. Okay, h1 we need to equate sigma h to 0. h1 is moving towards left. So equate this to rightward forces. That is 5 tons. So you are going to get the value as 5 each. So this is 5 kilonewton, 5 ton. R1 is also 5. R2 is also 5. See, I cannot start with this joint, 3 unknowns. This one, nothing is available. You can start, if you apply this, you get force in this member as 0 and this member as 0. Because no load is acting at the joint U2. See, these are all the things what you need to remember, because here at this particular stage, as far as possible, you must reduce your number of calculations. Right? Okay, now I consider equilibrium of joint L1. L1 I am going to consider equilibrium. There are 2 unknown forces and 2 known forces. Draw the free body diagram of this particular joint. So, coming to the equilibrium of joint L1. So, we will consider equilibrium of joint L1. Indicate all the forces, one horizontal member, a horizontal reaction H1. This is 5 tons, and a vertical reaction R1 is there. This is also 5 tons. Right? Now, assume the forces in the other 2 members. This member I assume compression. While I assume compression, my assumption should not go wrong. One vertical force is there at a joint in upward direction. Automatically, for equilibrium of joint, this member should contribute in downward direction. This member, see, 5 ton is moving out, so rightward force should be there. So this I call it as L1 U1, L1 L2, L1 L2, and this member I call it as L1 U1. Now apply the 2 conditions of equilibrium, that is sigma h equal to 0. Using sigma h equal to 0, rightward force equal to leftward force. So L1 L2 is equal to 5 tons. Is it tension or compression? See, arrow is moving away from the joint. Always away from the joint means it is tension. It was assumed to be tension, and also we got it positive 5 ton, that is tensile force. Again, equate sigma v to 0 equate resolve all forces in vertical direction and equate sigma v to 0. So if you equate sigma v to 0, downward force, that is F L1 U1, is equal to once again 5 tons, and it is compression. See, it is moving into the joint. Therefore, it is compression. So I can enter these values in the table immediately after analyzing a particular joint. F L1 and 2, L1 and 2. First one, it is 5 tension. Take positive sign for tension and negative sign for compression. F L1 U1, L1 U1, it is minus 5 tons. Immediately come to this particular figure, indicate the nature of force that you obtain. It is away from the joint. Again, here also it becomes away from the joint. Again, this was compression, downward, here it becomes upward. Right? Now consider equilibrium of next joint, that is U1. See, only U1 known forces. Force in this number is known to me. So now, if you consider equilibrium of this joint, draw the free body diagram. So one vertical force of magnitude 10 tons, a horizontal force is there of magnitude 5 tons. Then there is a force in the member in upward direction, that is once again 5 tons. There is a horizontal member, I don't know the force. Then there is a diagonal member. This angle is 45 degrees. Right. So force in this member, I call it as F U1 U2. And force in this member, I will take it as once again compression, that is into the joint. This I can name it as F U1 L2. F U1 L2. Okay. Now apply conditions of equilibrium for this particular joint. Now let us apply first sigma v equal to 0. So now F U1 L2 sine of 45. Resolve this force in vertical direction, it moves upward. F U1 L2 sine of 45 minus 10 plus 5. This force must be equal to 0. So from this determine F U1 L2. So you are going to get F U1 L2 as equal to 7.07. 7.07. And it is compression. Okay, if you simplify this, you get this as 7.07 tons, and it is compression. Right. Now equate sigma h to 0. Resolve all the forces in horizontal direction and equate them to 0. So F U1 U2, it is moving towards left, I assume. Right? So F U1 U2 minus this force, I got it 7.07 minus 7.07 cos of 45. Its horizontal component will be cos of 45 minus 5 plus 5. Okay, this is plus, this is minus 5 is equal to 0. So cos of FU1 U2 is equal to 5 minus 7 cos of 45. 7 cos of 45 works out to be 5. Therefore, FU1 U2 is equal to 0. So coming to this figure, this is a zero force member and this happens to be a compression member. This happens to be a compression. See, now we can write these two values here. FU1, U2, it is 0, then FU1, N2, FU1, N2, U1, N2, minus 7.07, minus sign because it is a compression number. Right. Next, two members are left out. Okay, we will consider equilibrium of this joint. There is no force at all. This is a zero force member. Let us say this member is FU2 N2, FU2 N2. This is a zero. Equals sigma B to 0. So automatically you get FU2 N2 as equal to 0. So this is also a zero force member. So FU2 N2 is equal to 0, you can write. Next number is FL1 U2. FL1 U2, there is no member, it is assumed to be resultant. So put a dash. See, we have completed one column of analysis for forces in the members except redundant by means of using method of choice. Now we will apply unit load in the direction of coordinate 1. Coordinate 1 was taken as this diagonal. Right? If I apply 1 kilonewton force here, what is the forces in the members? So now we will apply 1 kilonewton force in the direction. Okay, I will go for the next figure. Have a same type of figure because once again we need to analyze. So once again, I told us there will be one reaction. At this support also there can be a reaction, and there can be a horizontal reaction also. Force in this member, I assume this to be 1 kilonewton. Right? Force in this member, I assume this to be 1 kilonewton. Now, have this member also L1, L2, U1, U2. Okay. Now, we can consider a joint which has only two number of unknown forces. 1 kilonewton is acting like this. See, you need to consider the joint which has only two unknowns. If I consider this joint, I do not know these two reactions. Once again, I do not know the force in the member, this member. So, it will be a 4 unknowns. So, you cannot select that particular joint. Think of this joint, U2. Only two unknown force members are there. So, we can analyze this particular joint U2. So this is for development of the column, that is forces due to application of unit load at coordinate number 1. Right? So I consider joint equilibrium of joint U2. Right? Draw the free body diagram. One vertical member, then another horizontal member, then a diagonal member. And this angle happens to be 45 degrees. So, I assume forces in this member as, say, uh, F small l U2 L2 U2 L2 and force in this member I assume this to be compression and this I call it as F U2 U1. Call it as small l F U2 U1. Now apply conditions of equilibrium using sigma h equal to 0. I resolve this, it moves towards left. Force in this member, you can call it as FU1, FU1, U2. It is a normal, 1 kilo Newton. It is not 2. So, FU1 L1, you can directly write 1.0. I assume this to be a tension, so I will consider positive, 1.0. Now, equating sigma h to 0, F leftward, rightward force must be equal to leftward force. F U2 U1 is equal to 1 cos of 45. So check what is 1 cos of 45. So 1 cos of 45 means you are going to get cos of 45 equal to 0.707. So you get this as 0.707 kilonewton per ton. And is it compression or tension? See, it is moving towards the joint. Therefore, happens to be a compressive force. Similarly, use other condition of equilibrium, sigma v equal to 0. So, resolve all the forces in vertical direction and equate upward forces to downward force. FU2 L2, FU2 L2. It is upward. If I resolve this moves in downward direction is equal to FU1 U1 L1, FU1 L1, that is 1 sin of 45. Sin of 45 means it is nothing but once again 0.707 and check whether it is compression or tension. Moving towards the joint, therefore it is compression. So immediately you can write these values in the S1 column. FU2, U1, U2, FU1, U2. We got it as minus 0.707. FU1, U2, U1, U2, U1, U2 minus 0.707 minus sign because it is compression. FU2L2, U2L2, we got once again compression minus 0.707 minus 0.707. Okay, next consider equilibrium. See, here indicate the nature of forces immediately. This is the procedure what you need to do for analysis of truss. This is also a compression member, so indicate on both sides by compression. See, we determined 1, 2, 3 members. We will consider this particular joint. Consider equilibrium of joint U1 and draw the free body diagram of all the forces acting on this. Now considering equilibrium of next joint, that is joint U1, there is a horizontal force member, force in this member is compression, there is a vertical member and there is a diagonal member. So now, force in this member, I assume this to be a tension member. Why I assume tension means See, already one force is acting towards left, that I know. So, one of the horizontal component of this should act in rightward direction. See, this is how you need to assume the direction. Otherwise, what thing happens is, always you need to keep on changing the sign convention. So now, I will assume this to be upward. If this is rightward and it's one of the vertical component is downward, therefore to resist that, force in this member must be in upward direction. So namely this one, force in this member, we got it as the 0.707. This angle is 45 degree. Call force in this member as F U1 L2 and force in this member as F U1 L1. F U1 L1. Now apply the conditions of equilibrium. Sigma H equal to 0. So resolve all the forces. F U1 L2 cos of 45 must be equal to 0.707. 0.707. So find FU1 L2. So it is 0.707 divided by cos of 45. So 0.707 divided by cos of 45. You get 0.99 or 1.00, and it is outward, therefore tension. It is a tensile or positive force. Now apply second condition of equilibrium, sigma B equal to 0. Sigma B equal to 0. Now F U1 L1, F U1 L1, it is acting vertically upward. It must be equal to this component, F U1 L2 cos of 45. That is 1.0 cos of 45 degrees. Again, cos of 45 is 0.707. 0.707. It was assumed to be towards the joint. Therefore, it is compression. So, enter these two values in the table. FU1 and 2. U1 and 2. U1 and 2. Okay. It is 1.00. Minus or plus tension, therefore plus. FU1 L1, U1 L1, 0.705 compression minus 0.707. 0.707. Immediately indicate the nature in the main figure. One, it is tension, and this one is compression. Now, you can only one member is left out, right? So, I should find this one. I don't want to find these two reactions and all. I am not interested because it may take much time. Therefore, I go to this particular joint. Consider equilibrium of joint L2. Draw the free body diagram. Draw the free body diagram. So, now, considering L2, there is one vertical reaction R1 dash. You can call, but it is not necessary for me. So I cannot find that. There is a vertical force F U2 L2. So how much we got F2 L2? We got this as 0.707. 0.707 compression. I did not show minus there. Then there is a diagonal member inclined at 45 degree. I took this as And load force again tension 1.00. So I simply write its value 1.00 because I have already determined N2 U1. N2 U1. And again there is a horizontal member. Assume force in this member to be rightward. To be rightward. Call this as F L1 L2. Only this value is left out. So now equate sigma h to 0. Equate sigma h to 0. So F L1 L2 rightward force is equal to leftward component of this. That is 1.0 cos of 45. So you get once again 0.707. And this was assumed to be compression. Compression means towards the joint. So minus 0.707. See, now we need to go for development of the flexibility elements. To do that, we require S1 square, S1, S1. Let on we will find the net force. So, if you square this S1 square, for the first one you get 0.5, again plus 0.5, plus 0.5, plus 0.5. You can take your calculation. Again, this one is 1 and this one is also 1. S into S1. See, multiply S into S1. You are going to get minus 3.54. Then 0. This one you get plus 3.54. Minus 7.07. This one you get 0. Okay. See, now we will go for development of the flexibility matrix. Here only one redundant force is there, therefore your matrix size will be of 1 by 1. That's all. Means 1 only. So now displacement of coordinate 1, delta 1n is equal to sigma. Okay, before that, let us do one more calculation. See, determine sigma f1 square. It will be 4.0 sigma f1 square. This sigma you get minus 7.707. So these two values, find the arbitrary sum, find the arbitrary sum of these two columns. You get this one. So now delta 1L is equal to sigma S into S1 into L by AE. L by AE value, it is directly given to us. So this will be equal to L by AE is going to be 0.025. That is area by flexural rigidity. So into 7.07, you are going to get this as equal to minus 0.177. Similarly, displacement at coordinate 1 due to unit load at coordinate 1, small delta 1 is equal to sigma S1 square by into L by AE. Again, L by AE is given in the problem. In the problem itself, it is dictated. It is 0.025 into 4. That is sigma is 4. So you get this 0.01. 0.01 is the value. See, as I told you, since only one redundant force is there, we get a matrix of size only one by one row, one column. So now, force in the member P1 is equal to minus of delta 1 inverse into delta 1 So this is equal to minus delta 1 that is 0.01 inverse delta 1 we got it as minus 0.177. So if you use the calculator for analyzing the matrix, then you get the value of P1 as equal to 1.77. 1.77. Now to find the net force in the members, the equation is equal to S plus S1 into P1. S plus S1 into P1. See, now I will take each of the members separately and let us find the net force acting in each of the members. So now using that P1 we got it as 1.77 for the first member. Force in the first member F1 L2 is equal to 5 plus S1. S1 is minus 0.707 into P1 1.77. So this you are going to get it as 3.75. 3.75 tons, and it is tension. So 3.75 tons, and it is tension, therefore positive. For the next one, L2U2. S is 0 plus S1 is minus 0.707 into, okay, S1 is minus 0.707 into 1.77. So if you do it, you get minus 1.25. Minus sign indicates it is compression. Minus 1.25. Similarly, you can find the forces in all the members. So use the formula. A net force is equal to S plus S1 into P1. Up to P1 we have solved by flexibility matrix method. So now I will write directly the answer. The next one you get minus 1.25, 3.54. This one is minus 6.25, minus 5.30, 1.77. So, see, we have analyzed an indeterminate truss by means of flexibility matrix.